I decided to do my presentation on crystal structure, but since we already know a lot about crystal structure from Gen Chem, I figured I'd get more specific and do determining crystal structure. So one way to do this is by using X-ray diffraction, or X-ray crystallography. It's used to determine the separation of atoms, the distance between atoms, in a crystal by finding the distance between their planes. And I do this by seeing how the X-rays are diffracted by the crystal. Diffraction can only happen when the wavelength of radiation is about the same size as the object of interest. So because X-rays are so short in wavelength, they can actually be diffracted by the atoms in a crystal. And the diffraction patterns can be used to determine the distance between atomic planes. And if you determine the distance between atomic planes, then you can determine the distance between atoms, because they should be the same. So here you can see a representation of a crystal surface. The blue dots are the atoms, and they should be equidistant from each other. And the orange lines are the planes of the surface of the crystal. So the purple lines right here are X-rays coming in and being diffracted off of the atoms. However, because the X-rays are so small, some of them can pass through some atoms and hit atoms in a lower plane and bounce off there and be diffracted. So the distance between those two planes is d, and that's the distance we're interested in finding. So if we take a closer look at this area right here, so we would see those same two X-rays and those same two atomic planes. So we know that because the X-rays are coming from infinity distance away, that they have to be parallel to each other. And if they're parallel to each other and the planes are parallel to each other, these two angles are both the same, and we're calling those theta. We also know that the second X-ray gets diffracted after the first X-ray does, meaning that the second X-ray has to travel a little bit farther than the first X-ray. So it has to travel from A to B and B to C. So the path length difference is AB plus BC, because that's the distance it has to travel farther than the first X-ray. So we can define that distance using geometry. So we know that because this line is perpendicular to the X-ray and this angle is theta, that this angle also has to be theta. So we know that we could find the distance A to B if we just knew what this distance was here. Well, we're calling that distance D for now. So sine of theta is equal to the opposite, which would be AB, over the hypotenuse, which would be D. If we were to just solve for the distance from A to B, we would say A to B is equal to D sine theta. Now if we wanted to find the total path length, which would be this AB plus BC, we know that AB and BC are actually the same length. It's the same as saying 2AB, but we'll just write it out here. So if this is actually 2AB, then this turns into 2D sine theta. It's also important to note that the two X-rays have to be in phase with each other, both when they enter and exit the crystal after they've been diffracted. So for the X-rays to stay in phase with each other, that means that this path length difference, this AB plus BC, has to be some whole integer of the wavelength. So no matter what the distance is, it has to be any whole integer of the wavelength. So we can replace this AB plus BC with lambda, and then the equation becomes lambda equals 2D sine theta, which is actually known as Bragg's law. And the most common use for Bragg's law is to use it to calculate the distance between layers of atoms, which is actually the distance between the atoms themselves. So as long as you know the wavelength of your X-ray and the angle it hit the surface of the crystal, then you can very easily calculate the distance between those layers.